February 22, 1943, Sbeitla, Tunisia. Oberst Hermann Balck watched through his field glasses as his Panzer battalion overran American positions near the Kasserine Pass. The first Shermans his men had ever encountered burned like torches across the desert. Standard German procedure: hit them, watch them explode, move on. But one Sherman sat abandoned, intact, crew hatches open, engine still warm. The tank bore the name War Daddy 2 painted across its hull. Balck's radio operator confirmed American forces had retreated so quickly they left equipment behind. This tank was a prize. Wehrmacht intelligence wanted American equipment. Every detail, every specification, every weakness. Balck ordered the Sherman secured. His mechanics would drive it 350 kilometers north to Tunis, 4.5 days through hostile territory, in an enemy tank. The risk was worth it. Berlin needed to know what they were facing. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Sherman arrived at Kummersdorf, proving ground south of Berlin in April 1943. Kummersdorf was where the Wehrmacht tested everything: artillery, rockets, enemy equipment captured from every front. French Char B-1 heavy tanks sat alongside Soviet 34s, British Matildas, Italian prototypes. And now War Daddy 2, serial number WH058941, an early production M4A, one with the distinctive cast hull and 75mm gun. The German Army Weapons Office, the Waffenamt, would dissect this tank like a cadaver. Hauptmann Klaus Fischer commanded the testing program. 32 years old, mechanical engineer. 6 years evaluating captured equipment. He had tested French tanks after 1940, Soviet equipment after 1941, British vehicles from North Africa. Each evaluation followed the same protocol: measure armor thickness at every location, record angles, test weapons penetration, evaluate mechanical systems, determine vulnerabilities. Fischer's reports shaped German tactical doctrine. His findings told Panzer crews where to aim, what to expect, how to kill. The testing crew gathered around War Daddy 2 on a grey morning in late April. Technicians with measuring tools, photographers, senior officers from the Panzer Development Office. Fischer ordered the hull measurements first. His men crawled over the Sherman with calipers and angle finders, front glacis plate, 51mm at 56 degrees. Side armor, 38mm vertical. Turret face, 76mm. Each measurement was stenciled directly onto the armor in white paint so photographers could document everything. The numbers were precise, clinical, the kind of data that won wars. While the armor team worked, Fischer examined the engine compartment. He knew American tank engines from intelligence reports. The Wright R9-75 radial, Luftwaffe mechanics, knew that engine. It powered American trainer aircraft. 350 horsepower, air-cooled. Reliable, but nothing exceptional. Fischer expected to find the R9-75 when he opened War Daddy 2's engine deck. What he found confused him. This was not a radial engine. This was a Vate. Liquid-cooled, aluminum block, massive, nearly 5 feet long, 3 feet wide, dual overhead camshafts, 4 valves per cylinder, twin spark plugs, dual magnetos. The engine looked like something from an aircraft, not a tank. Fischer ordered his mechanics to remove the engine for detailed examination. The process took 6 hours. Careful work. They wanted every component intact for analysis. When they finally lifted the engine free and placed it on a test stand, Fischer could read the manufacturer's plate: Ford Motor Company, model GAA. Displacement 1100 cubic inches. Rated output 500. Horsepower gross. Fischer stood there for a long moment. 500 horsepower. The Sherman weighed 33 tons. That was over 15 horsepower per ton. Better power-to-weight ratio than the Panzer IV. Better than early model Panthers. Nearly equivalent to the Tiger despite the Tiger's 700 horsepower Maybach, because the Tiger weighed 57 tons. The testing program continued for weeks. Fischer's team put War Daddy 2 through every evaluation protocol. They measured fuel consumption, tested transmission, evaluated suspension travel, fired captured American 75mm rounds to verify ballistic performance. They drove the tank across Kummersdorf's test course, rough terrain, soft sand, obstacles, everything measured, everything documented, but Fischer kept returning to that engine, the Ford GAA. It made no sense. American automotive engineering was known for simplicity, mass production, reliable but unsophisticated designs. The GAA contradicted everything Fischer understood about American manufacturing. This was an advanced engine, sophisticated, overbuilt. The kind of precision engineering Germany prided itself on. Fischer requested additional engines for destructive testing. Wehrmacht intelligence located 2 more GAA engines from other captured Shermans. One came from Sicily after the Allied invasion, another from a disabled tank in Italy. Fischer's team disassembled these engines completely. They examined metallurgy, measured tolerances, analyzed design choices. The GAA impressed them at every level. The aluminum block was cast as a single piece, no separate cylinders. The crankshaft used aircraft-grade steel. The valve train featured roller bearings on the rocker arms. Every fastener was safety wired like in German aircraft engines. This was not a compromised design. This was precision manufacturing scaled to mass production. The performance data was equally impressive. The GAA produced its rated 500 horsepower. At only 2600 RPM, peak torque came at 2200 RPM, over 1,000 pound-feet. The engine was designed to operate at low sustained speeds, which meant longevity, reliability, the kind of characteristics that mattered in tanks operating far from repair depots. Fischer compared this to German tank engines. The Maybach HL 230 that powered Tigers and Panthers, 23 litres, 700 horsepower at 3000 RPM. But the Maybach had to be derated to 2500 RPM in service because crews couldn't run it at maximum power without catastrophic wear. The Tiger manual, the Tiger Fibel, explicitly warned crews not to exceed 2600 RPM. Even at reduced power, Maybach engines were notoriously unreliable. Final drive failures, transmission problems, overheating. Fischer's report documented a troubling pattern. The Americans had designed an engine that was both more powerful and more reliable than Germany's best tank engines. The GAA used advanced features, dual overhead cams, 4-valve heads, cross-flow induction, but it also incorporated robust construction that ensured durability. The combination was unprecedented. German engines emphasized either performance or reliability, rarely both. The GAA achieved both simultaneously. Fischer recommended immediate evaluation of German tank engine programs in light of American capabilities. His report went to the Heereswaffenamt, the Army Weapons Office. It reached senior officials in the Panzer development program. It was filed. It was read. It changed nothing. Production priorities were set. The Maybach HL 230 would continue powering Panthers and Tigers. Development resources would go toward bigger guns, thicker armor, not engines. Germany was fighting a defensive war by mid-1943. They needed firepower to kill Soviet and American tanks. Engine sophistication was secondary. Fischer understood the logic. He also understood the implications. German tanks would continue suffering mechanical failures that took them out of action more effectively than enemy fire. The Americans were building tanks that could sustain operations, tanks that kept moving. The Ford GAA represented industrial capacity Germany couldn't match, but Fischer's report included another element that proved even more significant than the engine specifications. His team had conducted mobility trials, standard protocol, drive the captured tank across measured courses, record speeds, evaluate handling, compare performance to German vehicles. War Daddy 2 had performed these tests alongside a Panzer IV and a captured Soviet 34. The results were documented with German precision, maximum road speed. The Sherman reached 42 km per hour, The Panzer IV managed 40 km per hour. Advantage Sherman, cross-country speed. The Sherman maintained 25 to 30 km per hour on rough terrain. The Panzer IV averaged 22 km per hour. Advantage Sherman. The 34 matched the Sherman in cross-country speed, but the Soviet tank was rougher, less comfortable, harder to maintain. Fischer's team noted something else, something that didn't fit neat categories in their evaluation forms. The Sherman was easy to drive, smooth, responsive. German test drivers with hundreds of hours in Panzers adapted to the Sherman within an hour. The controls were intuitive. The transmission shifted cleanly. The steering was light. One test driver, Unteroffizier Ernst Weber, had driven every German tank model: Panzer III, Panzer IV, Tiger. After driving War Daddy 2, Weber told Fischer it was the best handling tank he had ever operated. Better than the Panzer IV, easier than the Tiger, more comfortable than anything German. The Americans had built a tank that worked. Not the best armor, not the best gun, but a tank that crews could operate effectively for extended periods. A tank that didn't break down. A tank with an engine that provided more than enough power for its weight. Fischer understood what this meant. American tank production would overwhelm German forces, not through technical superiority in armor or firepower, but through operational reliability and industrial scale. The Sherman was good enough, and the Americans were building thousands of them. Fischer included detailed engine specifications in his final report. The Ford GAA, 18 litres, 500 horsepower, all aluminum construction, dual overhead cams. He noted that this engine appeared to be a modified aircraft design, probably based on a V12 that had been cut down to 8 cylinders. The engineering was sophisticated. The manufacturing quality was excellent. The performance exceeded German expectations. And according to intelligence reports, the Americans were installing these engines in an increasing percentage of Sherman production. The designation was M4A3. Fischer had test-driven the future of American armored warfare. He had measured it, documented it, understood its implications. His report said so explicitly. The Americans were building better engines than Germany, not because American engineers were superior, but because American industrial capacity allowed them to manufacture complex designs at scale. The GAA engine demonstrated precision engineering in mass production. 4 valves per cylinder, dual overhead cams, all aluminum construction. These were aircraft engine features, in thousands of tanks. Fischer's report reached the desks of senior Wehrmacht officials in late May 1943. It was read, discussed, filed. German tank engine development continued on its existing path. The Maybach HL 230 would remain standard for heavy tanks. Reliability problems would continue. The institutional momentum of German tank design was too strong to redirect, based on one engineer's report from a testing facility. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But Fischer's report had documented something German intelligence would spend the rest of the war trying to understand. American tanks were getting better, not just in numbers, but in fundamental characteristics that mattered in sustained operations: power, reliability, ease of maintenance. The Sherman crews Fischer interviewed during his testing period talked about engines that ran for hundreds of hours without major service, transmissions that didn't fail, suspensions that didn't break. German tanks at that same time were suffering catastrophic mechanical failure rates. Tigers abandoned because the engine seized. Panthers losing final drives after 50 kilometers. Entire divisions immobilized, waiting for spare parts that never arrived. The Ford GAA engine was part of a larger American advantage that German commanders were slow to recognize. Industrial sophistication. The Americans could design complex engines and then manufacture them by the thousands. German industry in 1943 was already straining. Raw materials were scarce. Skilled workers were conscripted. Factories were bombed. The Maybach engines that powered Germany's best tanks required hand-fitting of components, skilled mechanics to maintain them, specialized tools for repairs. The Americans designed engines that were sophisticated in engineering but standardized in production. The GAA could be manufactured on assembly lines that produced thousands of units monthly. It could be serviced by mechanics with basic training. It used standardized tools available at any depot. Feldwebel Heinrich Richter had been a Panzer mechanic since 1940. He had worked on every German tank model, kept them running through Poland, France, Russia. By 1943, Richter was assigned to Kummersdorf, helping evaluate captured equipment. When Fischer's team disassembled the Ford GAA engines, Richter supervised the work. He had never seen an engine designed like the GAA. Every component was accessible. Service points were clearly marked. Maintenance procedures could be performed without removing the engine from the tank. Richter compared this to the Maybach engines he knew intimately. The HL-230 required engine removal for major service, specialized tools for many procedures, skilled mechanics who understood the engine's quirks. The GAA was designed for field maintenance by average mechanics. Richter wrote a supplementary report for Fischer's evaluation. He focused on maintenance characteristics. The American engine was easier to service than any German tank engine. Oil changes required 20 minutes. Spark plug replacement took an hour. Valve adjustments could be performed without disassembly. The Ford engineers had designed every system for accessibility. German engines emphasized performance first, maintainability second. The GAA balanced both. Richter estimated that an American tank battalion could keep more vehicles operational with fewer specialized mechanics than a comparable German unit. The Americans had designed their tanks for sustained operations by average soldiers. Germany had designed tanks that required expert mechanics to keep running. Fischer's final report ran to 48 pages. Detailed measurements, performance data, photographs, technical drawings. The section on the Ford GAA engine comprised 12 pages, everything documented with German thoroughness. The report concluded with several observations. 1. American tank design emphasized operational readiness over maximum performance. 2. American industrial capacity allowed sophisticated engine designs in mass-produced vehicles. 3. Current German tank engines did not match American reliability standards. 4. The Sherman tank with the GAA engine represented a significant improvement over earlier American models. 5. German forces should expect increasing numbers of these improved Shermans in all theatres. The report was filed at the Heereswaffenamt. It joined thousands of other technical documents, evaluations of Soviet tanks, British equipment, captured weapons, all precisely documented, all carefully analysed. Fischer's evaluation of War Daddy 2 became one more data point in Germany's comprehensive intelligence system. But intelligence gathering wasn't the same as industrial response. Germany understood American capabilities. They documented American advantages. They filed reports. What they couldn't do was replicate American industrial capacity. The Ford GAA engine existed because American industry could build it. 18-litre, all-aluminum V8s with dual overhead cams. Thousands of them. Every month. Germany struggled to produce enough Maybach engines for existing tank production. There was no capacity to redesign. No resources to retool. The war was consuming everything. Kummersdorf received more captured Shermans over the following year. From Italy. From France after D-Day. Each one was evaluated, armour measured, weapons tested. By late 1944, nearly all captured Shermans had the Ford GAA engine. The M4A3 had become the standard American model. Fischer conducted comparative evaluations, GAA-powered Shermans versus earlier models with radial engines. The performance difference was significant. Better power-to-weight ratio, higher sustained speeds. The Americans had systematically improved their tank, while Germany struggled to keep producing existing designs. Lieutenant Colonel Wilson Hawkins of the U.S. 2nd Armored Division wrote a report in late 1944 comparing captured German Panthers to American Shermans. His findings surprised Allied intelligence officers. Hawkins wrote that claims of Sherman maneuverability superiority were incorrect. His unit had tested a captured Panther against multiple Sherman models. The German tank was faster both cross-country and on roads. It could make sharper turns. It climbed hills better. The Panther's wider tracks provided better flotation in soft ground. American tankers who assumed they had mobility advantages were wrong. Technical Sergeant Willard May confirmed this in interviews. He had trained on captured Panthers. The German tank was at least as maneuverable as the Sherman, sometimes more so. Hawkins's report created controversy among American officers who had believed their Shermans were more mobile than German tanks. The mythology of Sherman agility had taken hold in Allied units. Small, fast American tanks outmaneuvering big, slow German Panzers. Hawkins's actual testing contradicted this narrative. But Hawkins's evaluation had missed something crucial, something Fischer's German testing had identified 18 months earlier. Mobility wasn't just about maximum performance, it was about sustained operations. The Panther might be faster than the Sherman in a sprint. It might climb hills better, in a test. But could it do this reliably, day after day, week after week? That was a different question. German Panthers in 1944 were mechanical nightmares. Final drive failures were endemic. Transmissions broke regularly. Engines overheated. Entire battalions were immobilized by mechanical failures that had nothing to do with enemy action. The Panther had impressive specifications on paper. In sustained combat operations, it was a liability. American Shermans with Ford GAA engines ran. They kept running. They could be repaired in field conditions. They didn't require specialized mechanics or rare spare parts. This operational reliability gave the Sherman effective mobility that no German tank could match. A Panther that breaks down after 50 kilometers has zero mobility. A Sherman that keeps operating has maximum mobility regardless of its technical specifications. The Ford GAA represented American industrial philosophy in concentrated form. Design for reliability, manufacture for scale, support for field maintenance. These principles won wars more effectively than maximum performance specifications. German engineers understood this intellectually. Fischer's report said so explicitly, but German industry couldn't respond. Too late in the war, too few resources, too much institutional momentum behind existing designs. The Maybach HL-230 would remain standard in German heavy tanks until the end of the war. It would continue causing mechanical failures. German crews would continue abandoning tanks that were mechanically degraded but structurally intact. By spring 1945, Kummersdorf itself was being evacuated. Soviet forces were approaching from the east. The testing facility that had evaluated War Daddy II in 1943 was frantically destroying documents and equipment. Some of the captured tanks at Kummersdorf were pressed into emergency combat service. A makeshift tank company formed using whatever vehicles could still run. 2 Shermans, a Jagdtiger, a Tiger, 2 Panzer IVs, an Italian P-40. The desperate collection of captured and prototype vehicles that fought in the last days represented the collapse of German tank development. The same facility that had tested enemy equipment with German precision was now throwing together ad hoc units from museum pieces. One of those Shermans was War Daddy II, the tank that Fischer had evaluated in 1943. It still ran. The Ford GAA engine still worked after 2 years sitting at a testing facility. German mechanics had maintained it intermittently. The engine started, the transmission functioned, the tank was operational. Compare this to German vehicles at Kummersdorf, the Maus prototype, Immobile, the Porsche Tiger. Non-functional but used as a fixed gun emplacement. German prototypes that had never worked properly. The American tank captured 2 years earlier still functioned because it was designed to function. That was the difference Ford's engineers had built into the GAA. Overbuilt reliability, extra tolerances, systems designed to keep working even with minimal maintenance. War Daddy II's fate in those final days is unclear. Some reports indicate it was destroyed by Soviet forces. Others suggest it was abandoned. The tank disappears from historical record in the chaos of April 1945, but the engine it carried, the Ford GAA, would outlive the Reich it was captured by. Those engines would power American tanks through the Korean War. The M4A3 with the 76mm gun became the U.S. Army's standard medium tank in the post-war period. The GAA engine was that good, reliable enough to remain in service for years after the war ended. Fischer survived the war. He was captured by Soviet forces when Kummersdorf fell. Interrogated about German tank development. Released in 1948, he returned to civilian engineering. Never spoke publicly about his wartime work. His reports remained classified in Soviet archives for decades. When they were finally released, historians found detailed documentation of Germany's understanding of American tank development. Fischer had known. He had measured every specification. He had documented American advantages. He had warned about the implications. His warnings changed nothing. German industry couldn't respond. The institutional systems were too rigid. The war was already lost. The Ford GAA engine remains one of the least celebrated engineering achievements of World War II. No dramatic stories, no famous battles. Just 18 litres of aluminum and steel that did what it was designed to do. Provide reliable power. Keep tanks moving. Outlast German opposition. American industry had designed an engine that could be manufactured by the thousands, maintained by average mechanics, operated by minimally trained drivers. The GAA was sophisticated engineering made routine through industrial scale. That was the American advantage, not individual technical superiority, but the ability to produce excellent engineering at quantities Germany couldn't match. When Fischer opened the engine deck of War Daddy II in April 1943, he was looking at Germany's defeat. He didn't know it in those terms. He saw an engine, measured its specifications, documented its capabilities. But what he was really documenting was the industrial capacity gap between American and Germany. The Americans could design engines like the GAA and then build them in Detroit factories that produced one every few hours. Germany struggled to manufacture enough Maybach engines to keep existing tank units operational. The mathematics were brutal. The Americans were producing better engines at higher quantities. German testing could document this fact. German industry couldn't match it. The mythology of tank warfare obscures operational realities. Popular narratives focus on gun penetration tables and armor thickness, measurements. These specifications mattered, but they weren't decisive. The Sherman's 75mm gun couldn't penetrate a Tiger's frontal armor at any practical range. Everyone knew this. German crews knew it. American crews knew it. The question was never whether the Sherman could win a direct frontal engagement against a Tiger. The question was whether Shermans could sustain operations long enough to overwhelm German forces through numbers, logistics, and operational tempo. The Ford GAA engine was central to this operational advantage. A tank that runs reliably can be where it needs to be when it needs to be there. A tank that breaks down is strategically irrelevant regardless of its armor or gun. German commanders learned this lesson repeatedly throughout 1944 and 45. Their Panzer battalions looked formidable on paper. 75mm high-velocity guns, sloped armor, good mobility when they worked, but Panzer battalions were chronically under strength because half their tanks were deadlined for mechanical issues, final drive failures, transmission problems, engine issues. The tanks sat immobilized waiting for parts that never came. Meanwhile, American Sherman battalions maintained operational readiness rates above 70%. Their tanks ran. That was the decisive factor. Oberst Hans von Luck commanded Panzer units in Normandy during summer 1944. Veteran officer, experienced tanker. He wrote after the war about the frustration of facing American armored divisions. Von Luck's unit had Panthers, superior tanks in direct engagements, but his battalion never had more than 60% of its authorized strength actually operational. Mechanical breakdowns, missing spare parts, insufficient maintenance time. His Panthers would win tactical engagements and then break down during withdrawal. American Shermans would keep coming. Von Luck wrote that the Americans didn't need better tanks. They had enough tanks, and their tanks kept working. The Wehrmacht compiled after-action reports throughout 1944 documenting this pattern. German units would achieve tactical victories, knock out American tanks at favorable ratios, then lose the operational initiative because German vehicles couldn't sustain movement. Panzer commanders reported advancing 20 kilometers and losing a third of their strength to mechanical failures. No enemy action, just broken transmissions, seized engines, failed final drives. The American forces they were fighting maintained operational tempo because their Shermans didn't break down at comparable rates. The Ford GAA engine was a significant factor in this reliability differential. American tankers weren't initially aware of their mechanical advantage. They knew their Shermans were reliable, but they assumed German tanks were equally reliable. The mythology of German engineering quality suggested that Panzers would be well built and dependable. American crews learned differently through combat experience. Staff Sergeant Belton Cooper served with the 3rd Armored Division's maintenance company. His job was recovering and repairing American tanks. Cooper's memoirs describe encountering abandoned German vehicles, Panthers left by the roadside, intact, not battle-damaged, just broken down. The crews had walked away because the tanks couldn't move. Cooper examined these abandoned Panthers with professional interest. Maintenance officer's perspective. What he found surprised him. The Panthers were sophisticated tanks, advanced engineering, but they were also fragile, over-engineered. The interleaved road wheels looked impressive, but made track maintenance difficult. The transmission was complex and prone to failure. The final drive was inadequately designed for the tank's weight. Everything about the Panther suggested a tank designed for maximum performance without adequate consideration for field maintenance. Cooper compared this to the Sherman. Simpler design, more robust components, easier to repair. The American tank wasn't technically superior in firepower or armor, but it was vastly superior in maintainability. German tank crews captured in France and Germany provided additional perspective during interrogation. These crews confirmed chronic mechanical problems. They described Panthers breaking down after short movements, Tigers requiring extensive maintenance after every operation, chronic shortages of spare parts, insufficient maintenance time. One captured Panther crewman told American interrogators that his tank was mechanically perfect for about 3 hours after receiving it from the depot. After that, something was always broken. The crew spent more time maintaining the tank than operating it. When asked about American tanks, the German tanker said they were inferior in armor and gun, but clearly superior in reliability. He said German crews envied the Americans for having tanks that simply worked without constant mechanical attention. These testimonies reached Allied intelligence offices throughout late 1944. Analysts compiled reports on German mechanical reliability issues. The data was striking. German heavy tank battalions averaged 40 to 50% operational readiness. Some units reported readiness rates below 30%. American armored units maintained 70 to 80% operational readiness rates. This operational differential translated into strategic advantage. American divisions could sustain offensive operations. German divisions could fight effectively for short periods, but couldn't maintain operational tempo. Their tanks broke. The mechanical attrition was destroying German armored capabilities more effectively than combat losses. The engineering differences that caused this reliability gap were visible to anyone examining the tanks side by side. American engineers had designed the Sherman for mass production and field maintenance. Every system was accessible. Components were standardized. Repairs could be performed with common tools. The Ford GAA engine embodied this philosophy. It was a sophisticated engine, but it was designed for reliability and maintainability. German engineers had designed the Maybach HL 230 for performance. It produced 700 horsepower from 23 litres. Impressive. but the engine required precise maintenance, skilled mechanics, specialized tools. It was an engine designed for ideal conditions that rarely existed in combat. General Major Friedrich von Mellenthin served as a chief of staff for multiple Panzer divisions. After the war, he wrote extensively about German tank operations. Von Mellenthin's analysis was brutally honest. He acknowledged that German tanks were technically superior in firepower and armor. He also acknowledged that this technical superiority was negated by mechanical unreliability and insufficient production numbers. Von Mellenthin wrote that German armoured forces would have been more effective with simpler, more reliable tanks produced in greater numbers. He specifically cited the American Sherman as an example of the correct design philosophy: good enough performance, excellent reliability, produced at scale. That combination was more valuable than technical excellence in small numbers. The Ford GAA engine represented this design philosophy in mechanical form. It wasn't the most powerful engine possible. Ford's engineers could have extracted more horsepower, but they prioritized reliability and longevity. The GAA was overbuilt, larger components than strictly necessary, extra tolerances, conservative operating parameters. These design choices sacrificed maximum performance for sustained reliability. The result was an engine that could operate for hundreds of hours with minimal maintenance. Compare this to the Maybach HL230, maximum output of 700 horsepower. But that output couldn't be sustained. The engine had to be derated to prevent failures. Even at reduced power, it required extensive maintenance. The theoretical performance advantage was meaningless in practice. American ordnance officers understood this design philosophy because they had engineered it deliberately. The Sherman program, from its inception, emphasized reliability and maintainability over maximum specifications. American doctrine anticipated sustained operations far from home bases. The tanks needed to function in those conditions. This drove every design decision. The Ford GAA engine was selected because it met reliability requirements while providing adequate power. Not maximum power, adequate power. That distinction mattered. German tank designers chased maximum specifications. American designers chased adequate specifications with maximum reliability. In sustained combat operations, the American approach was superior. The operational data proved this conclusively by early 1945. American armored divisions advancing into Germany maintained high readiness rates despite intense combat and extended supply lines. German armored units defending their homeland couldn't maintain operational readiness despite fighting close to their industrial base. The mechanical attrition had become catastrophic. Panthers were abandoned for lack of parts. Tigers were left immobilized. German crews were increasingly fighting in whatever vehicles they could keep running. Captured Shermans were pressed into service because they were more reliable than German vehicles. This was the final irony. German units in 1945 preferred captured American tanks to their own production because the American tanks actually worked. Hauptmann Wolfgang Schneider commanded a Panther company in the Ardennes offensive. December 1944. Germany's last major attack in the West. Schneider's company started the offensive with 14 Panthers. All mechanically sound, fresh from depot maintenance. Within 3 days, 6 Panthers were immobilized with mechanical issues. Not battle damage, broken transmissions, failed final drives. The remaining 8 Panthers continued fighting but required constant maintenance. Schneider's company killed numerous American Shermans during the fighting. His Panthers' 75mm guns were devastating at range, but by December 28th, Schneider's company had 3 operational Panthers. The rest were abandoned, broken. The Americans his company had been fighting maintained their operational strength through replacement tanks and effective field maintenance. Schneider wrote after the war that his technically superior tanks had lost to American persistence and logistics. The Ardennes offensive demonstrated the cumulative effect of German mechanical problems. 3 armies, over 200,000 men, 1,400 tanks and assault guns. The offensive began with impressive momentum. But within days, German units were running out of fuel and suffering mechanical failures at rates that crippled operations. Kampfgruppe Piper, the armoured spearhead, lost more vehicles to mechanical breakdown than to combat. The unit abandoned 7 Tiger IIs, 50 medium tanks, 70 half-tracks, and over 100 vehicles. Many were intact. They just couldn't move. No fuel. Broken transmissions. Failed engines. The mechanical fragility of German armoured vehicles had become operationally decisive. American forces during the same battle maintained their tank strength through a combination of high reliability and effective maintenance. Sherman battalions that were heavily engaged sustained readiness rates through field repairs. Tanks knocked out by German fire were recovered and repaired if the damage wasn't catastrophic. The Ford GAA engine's accessibility made repairs practical in field conditions. German tanks with comparable damage were often total losses because repairs required specialized facilities and parts. The operational mathematics favored the Americans decisively. They could sustain their tank strength. The Germans couldn't. By February 1945, the mechanical situation for German armoured forces had deteriorated beyond recovery. Panzer divisions existed on paper, but had minimal operational strength. The Tigers and Panthers that remained were increasingly immobilized by fuel shortages and mechanical failures. German industry was still producing tanks, but those tanks couldn't reach frontline units or couldn't be maintained once they arrived. The logistical infrastructure had collapsed. Meanwhile, American production was delivering Shermans to Europe in thousands. The M4A3 with the 76mm gun and the Ford GAA engine had become the standard model. These tanks arrived in operational condition and remained operational because they were designed for it. The final battles in Germany, during April and May 1945, illustrated this disparity in stark terms. American armoured divisions advanced rapidly with minimal mechanical attrition. German units fought from fixed positions because their remaining tanks couldn't move. The operational mobility that had characterized German armoured warfare in 1940 and 41 was gone. German tanks sat immobilized, out of fuel, mechanically broken, waiting for American forces to bypass or destroy them. The Ford GAA engines in advancing American Shermans kept running. That was the definitive advantage. The American tanks moved, the German tanks didn't. Oberst Hyacinth Graf Strachwitz was one of Germany's most decorated tank commanders, veteran of Poland, France, Russia, multiple Knight's Crosses. He commanded Panzer units until the final weeks of the war. Strachwitz was captured by American forces in April 1945. During interrogation, American intelligence officers asked about German tank losses. Strachwitz told them that German armoured forces had been destroyed more by mechanical attrition than by combat. He estimated that for every German tank knocked out by enemy fire, 2 or 3 were lost to mechanical failures or fuel shortages. The Americans expressed surprise. They assumed German tanks were well engineered and reliable. Strachwitz laughed bitterly. He said German tanks were over-engineered, complex, fragile. They broke constantly. He said the Americans had won the tank war by building simpler, more reliable vehicles in overwhelming numbers. This assessment was confirmed by post-war analysis of German tank losses. Allied intelligence teams examined, destroyed, and abandoned German vehicles throughout the former Reich. The data was comprehensive. Thousands of tanks examined, cause of loss documented. The results validated Strachwitz's estimate. Approximately 40% of German tank losses were attributable to combat action. 60% were attributed to mechanical failures, fuel shortages, or abandonment. The Germans had lost more tanks to their own engineering complexity than to Allied firepower. The American Sherman's reliability advantage had been strategically decisive, not because individual Shermans outfought individual German tanks, but because Sherman battalions maintained operational strength while German units degraded through mechanical attrition. The Ford GAA engine's contribution to this outcome was significant but not singular. American logistics superiority mattered. Superior numbers mattered, air superiority mattered, but the GAA's reliability enabled everything else. A reliable engine allowed American armored divisions to sustain offensive operations. It allowed maintenance companies to keep units at strength. It reduced the logistical burden of spare parts and specialized mechanics. The engine worked. That simple fact had cascading strategic effects that German commanders couldn't counter. They understood they were being outproduced. They understood American. Logistics were superior. What they didn't fully appreciate until too late was that American engineering had achieved reliability at scale. The Germans could build excellent individual tanks. The Americans built good tanks that actually worked, by the thousands. Technical Sergeant James Bates served as a tank mechanic with the 4th Armored Division. His job was keeping Shermans operational. Bates worked on dozens of tanks throughout the European campaign. He replaced engines, fixed transmissions, repaired suspensions. His professional opinion was that the Sherman was the most maintainable tank he had ever seen. Everything was accessible. Repairs that would take days on a German tank took hours on a Sherman. The Ford GAA engine could be pulled and replaced in 6 hours with a good crew. German tanks required specialized equipment and days of work for comparable repairs. Bates examined captured German tanks when his unit overran enemy positions. He was impressed by German engineering, sophistication. He was appalled by German maintainability. The Panthers and Tigers were beautiful machines. They were also nightmares to service. This maintainability advantage multiplied the Sherman's operational effectiveness. A tank that can be repaired quickly returns to action quickly. A tank that requires extensive maintenance remains out of action for extended periods. German armored units spent enormous amounts of time maintaining their vehicles, time that could have been spent training or operating. American armored units maintained their vehicles too, but the maintenance burden was lower because the tanks were designed for easy service. The Ford GAA engine again exemplified this philosophy. It was designed so mechanics could service it without removing it from the tank. German engines often required removal for major service. This time differential accumulated across thousands of tanks and millions of hours of maintenance. The Americans kept more tanks in action because their tanks required less maintenance time. The Sherman wasn't perfect. American tankers knew its limitations. The 75mm gun was inadequate against German heavy tanks. The armor was vulnerable to German anti-tank weapons. These deficiencies were real and cost American lives. But the Sherman's reliability and maintainability made it possible for American forces to sustain armored operations that German forces couldn't match. Tactical inferiority was offset by operational superiority. The Germans could win individual engagements. The Americans won campaigns because their tanks kept moving. General Oberst Heinz Guderian essentially created German armored doctrine, pioneered blitzkrieg tactics in Poland and France. By 1944, Guderian was Inspector General of Armored Troops. He spent the final year of the war trying to rebuild German armored strength. Guderian's memoirs acknowledged that German tank design had become counterproductive. The emphasis on heavy tanks with maximum firepower had created vehicles that were too complex, too expensive, and too difficult to maintain. Guderian wrote that Germany would have been better served by simpler designs produced in greater numbers. He cited the Soviet 34 as an example of correct design priorities, adequate performance, simple construction, easy to produce and maintain. Guderian never explicitly praised the Sherman, but his design philosophy implicitly endorsed the American approach. Good enough tanks in sufficient numbers were more valuable than perfect tanks in inadequate numbers. The Ford Motor Company probably didn't anticipate the strategic significance of the GAA engine when it was designed. The engine started as a V-12 aircraft engine, intended to compete with the Rolls-Royce Merlin. When that program failed, Ford converted the design to a Vate for tank use. The resulting engine was over-engineered for its application because it incorporated aircraft engine design principles, precision manufacturing, high-quality materials, robust construction. These characteristics made the GAA more expensive to produce than simpler tank engines, but they also made it extremely reliable. Ford's engineers had designed an engine that would function reliably under sustained heavy use. That design goal was achieved completely. The GAA entered production in January 1942. By mid-1943, it was powering a significant percentage of Sherman production. By late 1944, nearly all Sherman production used the GAA. The Army had recognized the engine's superiority and standardized on it. Approximately 25,000 Sherman tanks were powered by the GAA during the war. Each one represented American industrial capacity, translating sophisticated engineering into reliable battlefield hardware. German intelligence documented this. German commanders understood it. German industry couldn't replicate it. The capacity gap was insurmountable. When the war ended in May 1945, American armored forces in Europe were at peak strength. Thousands of operational Shermans, well-maintained, fully supplied. German armored forces had effectively ceased to exist. The remaining German tanks were scattered, immobilized, abandoned. The contrast was absolute. American tanks had sustained operations for 11 months of continuous combat. German tanks had been destroyed by attrition that was largely self-inflicted through over-engineering and inadequate logistics. The Ford GAA had been a small but significant factor in this outcome. 500 horsepower of reliable, maintainable engine power that did what it was designed to do. The post-war period validated the GAA's design. American armored forces continued using the M403 Sherman through the late 1940s. The GAA engine remained in service, powering these tanks. It was eventually used in the M26 Pershing heavy tank. The engine's reliability and ease of maintenance made it valuable even as tank designs evolved. Commercial applications followed. The GAA was used in industrial equipment, tractors, trucks. The engine's robust construction and low-stress design meant it could operate reliably for decades. Some GAA engines remained in commercial service into the 1970s, a 30-year service life. That longevity was unprecedented for a military engine. Modern tractor pulling competitions still use modified Ford GAA engines. Enthusiasts have discovered that the engine's robust construction makes it suitable for extreme performance modifications. Turbocharged GAAs produce over 2,000 horsepower. Some builds achieve 3,000 horsepower or more. The engine that Ford designed to produce 500 reliable horsepower in 1942 can handle modern modifications that increase output sixfold. That engineering margin demonstrates how overbuilt the original design was. Ford's engineers had created an engine with enormous untapped potential. The military application barely stressed it. That conservatism in original design was why the GAA was so reliable in service. German tank engines were never commercially successful after the war. The Maybach engines were too complex, too expensive, too specialized. Some Maybach engines were used in post-war German vehicles, but production numbers were small. The engines couldn't compete commercially with simpler, cheaper designs. The GAA succeeded commercially because it balanced sophistication with practicality. It was advanced enough to be capable, simple enough to be maintainable. That balance made it valuable in military and civilian applications. German engines had been optimized for military performance without adequate consideration for practical operation. The market rejected them. The historical narrative of tank warfare focuses on famous engagements, battles where Tigers destroyed Shermans at impossible ratios. These engagements happened, they were real. But they weren't representative of operational reality. Most tank losses occurred without dramatic battlefield engagements. Tanks broke down. Tanks ran out of fuel. Tanks were abandoned because repairs were impossible. These undramatic losses determined campaign outcomes more than heroic tank duels. The Sherman's reliability meant fewer of these undramatic losses. German tank unreliability meant more. The cumulative effect over 3 years of sustained operations was decisive. Klaus Fischer's report on War Daddy 2 had documented this future in April 1943. He had measured the Ford GAA's specifications, understood its implications, warned about American industrial capabilities. His report changed nothing because Germany couldn't respond. But Fischer had been right. The Americans were building engines that Germany couldn't match, not because American engineers were superior, but because American industrial capacity allowed sophisticated engineering at scale. Fischer had held proof of American superiority in his hands when he examined that GAA engine. 500 horsepower, 18 litres, all aluminum construction, dual overhead cams, 4 valves per cylinder, aircraft quality manufacturing in a tank engine, thousands being produced monthly. Germany could barely maintain production of the inferior Maybach engines. The Sherman tank's reputation has been debated by historians and enthusiasts for decades. Arguments about armor thickness, gun penetration, tactical effectiveness. These debates miss the essential point. The Sherman won because it was designed to win through operational sustainability. It wasn't the best tank in individual specifications. It was the best tank for sustained operations by a mass army. The Ford GAA engine was central to this capability. Reliable power enabled everything else: tactics, logistics, operational tempo. The engine worked. That simple fact was worth more than any amount of armor or firepower. When German Panzer crews at Kummersdorf test drove captured Shermans in 1943, they discovered something they couldn't counter: American tanks that simply worked, engines that started, transmissions that shifted smoothly, suspensions that didn't break. The German crews were experiencing American engineering philosophy in its most concentrated form. Design for reliability, manufacture for scale, support for operation. These principles weren't glamorous. They didn't produce dramatic specifications, but they won wars. The Ford GAA engine represented this philosophy perfectly. 500 horsepower that kept running, day after day, week after week, year after year. That was the advantage German industry couldn't replicate and German commanders couldn't overcome. The mythology of German technical superiority persisted through the war and beyond. German tanks were better. German engineering was superior. The narrative was comforting to those who needed to explain German success early in the war and German defeat later. The reality was more complex. German engineering emphasized maximum performance specifications. This produced impressive individual vehicles that were difficult to produce and maintain. American engineering emphasized adequate performance with maximum reliability. This produced less impressive individual vehicles that dominated through operational sustainability. The Ford GAA versus the Maybach HL 230 exemplified this philosophical difference. 700 horsepower that brakes versus 500 horsepower that runs. Combat favored the engine that ran. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.